let's say, a speaker. I'm very pleased to introduce Dr. Sushmita Das, who is my fellow co-chair at the YO Executive Committee Working Group for Junior Members. She obtained her PhD at the University of Delhi in 2022, then pursued her first postdoc at the Konkoly Observatory in Budapest in 2024. And now she is following her second postdoctoral position at the Inter-University Center for Astronomy and Astrophysics, which we usually call as AYUCA, collectively speaking. And her broad research is actually revolving around pulsating variable stars and their applications to the cosmic distance scales. And I know that Sushmita does a lot of multi-wavelength range astronomy, which is one of the very hot topics. And like combining that with time domain astronomy, I believe has a lot of value. And she's using and leveraging the data coming from the landmark mission Gaia mission and the ground-based facility OGIL. And she combines these observational data with the models from MESA that a lot of us use for very different purposes. So thank you so much for your participation today, and I'm giving the floor to Dr. Das, our lovely Sushmita. And please go ahead, share your screen. Thank you so much again for accepting our invitation. We're very much looking forward to talk.
Thanks. Is everything visible? The
Yes,
slides?
perfect.
Okay.
Perfect.
Hi, everyone. Thank you for being here today. Thank you, Fatime and Julia, for inviting me to this wonderful seminar series. I'm Sushmita, a postdoc at AYUCA, previously at Konkoly Observatory, Budapest, and today I'll be talking about BL Herculis stars. So you may not have heard about BL Herculis stars, but I'm pretty sure you have heard about Cepheids, in particular classical Cepheids. So classical Cepheids are population 1 stars, and type 2 Cepheids are its population 2 counterparts. So BL Herculis stars are simply the shortest period type 2 Cepheids. So of course we will be looking into this a bit more in the coming slides.
Jasmita, I can see your next slide. Just a moment. Are you scrolling these slides or not? Because I see your first slide.
The cover slide?
Yeah.
Yeah.
Okay, now I'm in slide 2.
Okay, perfect. Sorry. Okay.
Perfect.
Okay.
Thank you.
So this talk is based on a series of 4 papers so far titled A Theoretical Framework for BL Herculis stars, where we have been looking at the effect of metallicity and convection parameters on different theoretical relations. The first 2 papers dealt with the Johnson-Cousin band and the Gaia passbands, and the most recent one extended this study to the Rubin-LSST filters. A brief introduction on classical pulsators. This is the HR diagram showing the various kinds of pulsating variables across different evolutionary stages. This line right here is the main sequence. The dashed line over here is the horizontal branch, where stars are burning helium in its core. And the narrow range right here, enclosed by the dashed lines, is called the classical instability strip. It is characterized by a whole range of luminosity across the HR diagram, but constrained over a very narrow effective temperature range. So all of these stars or classes of stars that are constrained between this classical instability strip are called classical pulsators, and they all pulsate because of the same mechanism, which is called the kappa mechanism. Here, I would like to highlight the famous classical pulsators, the RR Lyrae, which lie at the intersection of the horizontal branch and the instability strip. Delta Cepheids or classical Cepheids, which are higher up because they are more luminous, and intermediate to RR Lyrae and classical Cepheids lie the type 2 Cepheids. And as mentioned, one subclass of type 2 Cepheids, the BL Herculis, lie here, intermediate to RR Lyrae and Delta Cepheids. So why are they so important in stellar astrophysics? This is because every classical pulsator follows a well-defined period-luminosity relation that can be used to estimate extragalactic distances. So, for example, in this figure, you see all the different classes of classical pulsators All of these obey well-defined period luminosity relations. However, they all follow different PL relations from one class to the other. For example, in particular, if I highlight classical Cepheids versus the PL relation that is followed by type 2 Cepheids, they are clearly on different PL relations. This is also useful to separate out different classes during classification. First, of course, the highlight is that type 2 Cepheids obey a different PL relation from classical Cepheids. And then the second one is type 2 Cepheids seem to follow the same PL relation as followed by the RL stars. This will be useful, which I will be talking about a bit later. Now, so why did we choose to study type 2 Cepheids from a whole spectrum of classical pulsators? What makes them so special that is not seen in other kinds of classical pulsators, RL and classical Cepheids, for example? So first, coming back to type 2 Cepheids, they are subclassified into BL Herculis stars, W Virginis stars, RV Tauri stars. The simplest convention is that they are divided in classified as per their pulsation relations. So BL Herculis stars are the shortest period type 2 Cepheids with pulsation periods of 1 to 4 days. Now, as was seen from the HR diagram, because they lie intermediate to RL Iris and classical Cepheids, they are brighter than RL Iris, but fainter than classical Cepheids. So this comes handy when we are talking about regions in the sky, for example, say where there are scarce RL Iris, right? Or so they are very important to fill in the gap where our lyres might not be present or classical Cepheids where classical Cepheids might not be present, right? So they very efficiently fill in the gap between our lyres and classical Cepheids. Just like the other classical pulsators, they follow well-defined period luminosity relations. However, when we started this work back in 2020, so this is not the extensive literature survey, but we will compare all of the available literature towards the end of this talk. So when we started this work, it was very surprising that compared to hundreds of papers, both theoretical and empirical on our lyres and classical Cepheids, there were extremely few research that was being done on type 2 Cepheids. On both theoretical as well, most promising features that type 2 Cepheids exhibit is that they seem to show negligible or no metallicity dependence on the PL relations. Now, why is this significant? Because most of the studies now, if you've ever heard of talks with classical Cepheids, one of the most important research that is being done in that area is trying to calibrate the effect of metallicity on the PL relations. So in that respect, if we have type 2 Cepheids that offers the promise of weak or negligible effect of metallicity, it is a game changer in the entire field of how we estimate extragalactic distances, for example, without having to take care of the uncertainties involved in the metallicity estimations, right? Now, coming to why am I talking about BL Herculis stars in particular, when we should in fact be talking about type 2 Cepheids as a whole. So this is a current limitation of the stellar pulsation aspect, where we can reliably model BL Herculis and the shortest period W Virginis. The current codes, the current existing pulsation codes do not do well with longer period W Virginis stars and RV Tauri stars. So ideally, of course, we should be dealing with the entire BL Herculis, W Virginis, RV Tauri together when we are talking about type 2 Cepheids. But of course, this can be supplemented by more observations over all three categories when we are talking about type 2 Cepheids as a whole. Now, coming to the data. So hopefully I have convinced the audience why type 2 Cepheids are such important astrophysical objects and worthy of our attention. So now we talk about what kind of data is being used. So first, I use a lot of, I extensively use MESA-RSP. Just like all other existing stellar pulsation codes, it has its advantages and disadvantages. But one of the most important advantages I would like to highlight is that MESA-RSP is an open source code, and it believes in making inlays transparent. So all of the physical parameters that are used to code these models are made public so that it is reproducible. So, and then we have a lot of other parameters, of course, which should be changed, but reasonably. So here I would like to highlight two examples. On the right, we have an RLI model where so the black dots are observed points and the solid lines are from the models. On the topmost, the top panel has the light curve, whereas the lower panel has the radial velocity curves. As is visible, it does quite a good job in simultaneously fitting both the light curve as well as the radial velocity curve. On the left, you see a type 2 Cepheid, also with a feature. So this is not the typical sawtooth light curve feature, but also that exhibits something like a pump. And MESA-RSP quite reliably also tries to capture the bump feature in the light curve structure. So now this is where my work comes in. So what we did was we did BL-Her, so we compute a grid of BL-Her models. The two key parameters that we wanted to study were the effect of metallicity, of course, which is our primary goal, and secondly, the effect of convection parameters. For this metallicity, we have a wide range of metallicity over 7 different values. Stellar mass, we vary from 0.5 to 0.8 solar mass, going a bit higher than what is expected literature values. Stellar luminosity from 50 to 300 solar luminosities in steps of 50. Effective temperature in steps of 50 Kelvin to capture the instability strips. So all of these combinations result in 20,000 models per convection set. So 20,000 multiplied by 4, right? So this would be computationally very expensive. So before we move to nonlinear computations, we want to make sure that we only compute potential BL-Her models. For that, first we compute the linear computations. From there, we get two things. One is the edges of the instability strip, so the red edge and the blue edge. So anything that lies between the instability strip shows positive fundamental growth rate. Anything beyond the instability strips have negative growth rate. Now, next, once we have identified the region of pulsation, next we move on to the linear periods. So the dashed lines that you see over here represent 1 to 4 days, which is typical for BL-Her models. So the area of intersection are potential BL-Her models. So as soon as we make these cuts using instability regions and the pulsation periods, we are left with about 4,000 models per convection set. So this already drastically cuts down our model number. So for all of these 4,000 models per convection set, we allow it to undergo nonlinear computations. But before accepting that as a BL-Her model, we have to do certain checks. For example, here in this case, we see a figure where they have the same input parameters. So Zx are the chemical composition, mass, luminosity, and temperature, right? So all of these four, set A, B, C, and D, refer to different convection sets. And then they all have the same input parameters, Zx, MLT. Now, as is visible from the plot, so you see that they behave quite differently. So convection indeed plays a very significant role in pulsation models. Now, before we proceed to accept a model as to be used for analysis, we have to check for what is called a full amplitude stable pulsation condition. For this, we check 3 parameters, delta R, which is the change of radius from cycle to cycle, P, which is the pulsation period, and gamma, which is the growth rate of kinetic energy from cycle to cycle. We want to make sure that these stabilize. So mathematically, it translates to they do not vary for a total of 4,000 pulsation sample. This particular example, once again, we had the exact input parameters. The only difference was convection parameter sets. So from this figure, set A, B, and C, the models are accepted for further analysis, while we reject D because they do not stabilize over the last 100 cycles. Now we also, the output from MESA-RSP is the bolometric luminosity, which has to be transformed to individual passbands. So for Johnson-Cousin bands, we use pre-computed bolometric correction tables that has already been included in MESA. And this is how the light curves look like. For Gaia, we have MESA-RSP also provides custom-bred tables to be incorporated. So we use bolometric correction tables first from MIST, and then so here is the reference from how the bolometric correction tables were computed suitable for Gaia passbands. And this is how this for one particular model, this is how the light curves look like over different passbands. Lastly, so we also, in our most recent study, we provided the first theoretical relations for BL Hertz stars in Rubin-LSST and the theoretical light curves. So once again, we used custom input bolometric correction tables to transform the bolometric light curves to the appropriate Rubin-LSST bands. So I will briefly touch upon this on why we are talking about empirical data from Gaia DR3. But this is what will be used in like in a couple of slides for comparison of light curve structures. I will come back to why this is important. For the methodology, what we do is, of course, for the observed light curve, we phase the raw light curves. For both observed and theoretical, what we do is we fit the phased light curve with a Fourier sine series of this form. So wherever we talk about mean magnitudes, we don't use a simple mean. We use the mean that is obtained after fitting the phased light curve with a Fourier sine series of the form as mentioned here. Then to quantify the light curve structure, we also use what is called the Fourier parameters. So after fitting Fourier sine series, we get AK and phi k, which are the Fourier amplitude coefficient and the Fourier phase coefficient. So RK1 is the Fourier amplitude parameter, which is a ratio of the Fourier amplitude coefficients. And phi k1 is the Fourier phase parameter, which is a difference of the phase coefficients. So coming to the results, here we have the Rubin-LSST directly. Instead of going over all of the passbands, we will look into how all of the passbands look like at a glance later on. But a brief moment here. So this is the period luminosity relation. So on the Y, you have all of the Rubin-LSST bands, R, I, Z, and Y. On the X-axis, we have the log of P. Appropriate for the BL Herculis models. Our main intention, what we wanted to start with was to study the effect of metallicity, right? So two very important results stand out here. First, if you look here, R Lyrae first overtone and R Lyrae fundamental. You see there is a split in the lines. Different colors represent different metallicities. So when you see the split in the line, it is very obvious that different metallicities obey slightly different period luminosity relations. So this is a direct indication that there is an effect of metallicity on the period relations. On the other hand, when you look at BL Herculis stars, these also have the exact same 7 chemical compositions as is represented in our array. But here you do not see the spread or the split anymore, which means that theoretically, for the Rubin-LSST passbands, we find that there is negligible effect of metallicity on the period-luminosity relations. The second point is that, as was discussed prior, so classical Cepheids and type 2 Cepheids obey very different PL relations. However, type 2 Cepheids follow, they seem to follow a continuous PL relation to RL arrays, as can be seen here, right? So they seem to follow the same PL relation. So this is important because they can be used as an independent PL. So classical Cepheids have a whole PL relation, whereas all of the population 2 can be used together to follow an alternative distance ladder. So RL arrays, type 2 Cepheids, and tip of the red giant branch as an alternative to the classical Cepheids. Now, so this is all of the different passbands. So on the x-axis are all of the bands. So the capital U, B, V, etc. are the Johnson cousin. Of course, we also have the Gaia, G, GBP, GRP, and the small U, G, R, I, Z, and Y represent the Rubin-LSST bands. So this is the entire range of passbands that we have theoretical data for. On the y-axis is gamma, which is the effect of metallicity, the metallicity coefficient term. So the important result to highlight here is that anything that is longer than, say, for example, V has negligible gamma value. So all of these values are somewhere about 0, right? So once again, in contrast to RR Lyrae and classical Cepheids, which are known to exhibit strong metallicity effects on the PL relation, we see that BL Her models predict negligible metallicity contribution to the PL relations. Now here, U and B, this is also seen in observed empirical relations. That also has to do with the fact that the bolometric corrections are more sensitive to metallicities at wavelengths shorter than V-band. Now, most of the studies, so going back to why it's important to compare light curve structures using the Gaia DR3, for example. So most of the relations provide mean period luminosity relations, mean period radius relations, mean period Wesenheit relations, for example. So it's very useful, of course, to provide PLZ relations because that is easy to compare with observations. However, we have to remember that these are classical pulsators, so they do vary their light curve structure. They have changes throughout their pulsation cycle. So when we use mean period relations, we sort of average out the entire pulsation cycle. So we have to make sure that whatever models we are computing, it's very easy to provide the PLZ relation, for example, but we have to make sure that whatever models we are computing do match well with the observed light curve structure, right? So this is not at all trivial. This was extremely hard, but we have very promising results at this end. So what we did was we did what is called a light curve model fitting approach. We used previous optimization techniques as was used by Smolek and Joyce. We have to use the conditions of constraining the pulsation period first, because one of the most well-studied parameter for classical pulsator is its pulsation period. So we have to make sure that the observed pulsation period and the theoretical pulsation period are very close to each other. Next, the D parameter tries to minimize the offset between the model light curve and the observed light curve. And then we have a whole range of parameters over the pulsation period, the amplitude, the skewness, acuteness, and like we mentioned earlier, R21, R31, Phi21, Phi31, which are which quantify the light curve structure. So we have to make sure that one, the pulsation period do very well with respect to each other, and second, the light curve structure are very close to each other. So using these constraints, we have a gold sample of 30 model observed pairs. So, of course, we also have to deal with a lot of uncertainties and degeneracies. So it could be like one observed star, for example, corresponds to 10 models. So how do we choose which one is the best model, right? So of course, to break down the degeneracies further, we have to incorporate multi-band simultaneous fitting, radial velocity curve fitting if possible. Metallicity, of course, significantly helps in this respect because we cut down a whole subset of what we want are matched. So the model, if we already have a very clear idea of what the metallicity is, we can use that particular metallicity of models to begin with our matches, right? But in any case, this is what we provide. This is our gold sample of matches. And so the red ones are the observed data, and the blue ones are from our models. You can see that it fits not only the classic sawtooth light curves well, it also tries to fit in a couple of bumps. So what we did was, this is pretty decent. And what we then use is once we are satisfied that our models do well not only with respect to the mean period luminosity relations, but also with the light curve structures and pulsation periods, we move on to estimate the LMC distance. And what we have is 18.582, which is reasonably close to what Wielgorski had estimated using type 2 Cepheids. This is my summary slide. I would just, very brief. So in the series of 4 papers, what we had done is we had computed an extensive grid of BL Herc models over Johnson-Cousin, Gaia, Rubin-LSST, mainly to study the effect of metallicity. And what we found was very promising, that theoretical PL relations exhibit negligible metallicity effect, which offers us a huge advantage over what is predicted and seen for RLRs and classical Cepheids, right? I would now like to take a brief moment of how does it make sense in the context of WST. So if you have attended classical pulsator talks, you are familiar with this distance ladder scale already. So what this does is there are 3 rungs here. So first, it calibrates the PL relation using Cepheids and the parallax. The next rung takes host galaxies where you have both Cepheids and supernova type 1a. And then the third rung estimates the local Hubble constant from the distance redshift, the slope of the distance redshift relation. Now, we also have an equivalent type 2 distance ladder using RLRs, type 2 Cepheids, tip of the red giant branch, which is not included in this slide. Why is that useful? Because the first, whatever error will be introduced here is propagated towards the other rungs. So the first, we have to be extremely thorough with the error budgets that are error that may be introduced in the first rung. And type 2 Cepheids or population 2 counterparts are very important for an independent check, right? So to make sure that the calibration of PL is okay. Now, type 2 Cepheids here will provide an advantage because, as mentioned, classical Cepheids and RLRS stars have metallicity dependence. So if type 2 Cepheids can be used, that promises negligible metallicity dependence, it can be very useful as an independent check to the distances estimated by classical Cepheids. So here I would like to summarize all of the relations so far. This is not complete. It has one literature missing. So Marconi and team had recently published a paper for type 2 Cepheids in multiple wavelengths from the theoretical perspective. So only that literature remains to be added. But here is an extensive comparison of everything that is available in the literature so far. So a lot of things happening here. So very quickly, on the x-axis, once again, we have all of the wavelengths in increasing, all of the passbands in increasing wavelength over Johnson-Coulson, Gaia, ZTF, Rubin-LSST. On the y-axis, we have the gamma, which is the metallicity coefficient term. The topmost panel represents the BL Her subclass only. The second panel, W Virginis. The third panel, Arvitori. The fourth panel combines BL Her and W Virginis together. And lastly, the lowermost panel talks about, demonstrates type 2 Cepheids combined. So BL Her plus W Virginis plus Arvitori. Now, all of the solid points, all of the circles that you see here are from empirical results. So wherever you see solid circles are the empirical gamma terms, whereas all of the stars are from theoretical estimates. Now, of course, the obvious thing is we are missing out on quite a few observed points, right? And in this regard, WST can play a significant role, and a tremendously significant role, because it is very important to have a homogeneous spectroscopic metallicity determination so that we can really close down on the weak metallicity, negligible metallicity that is promised from the theoretical perspective. So we do have a couple of empirical relations that seem to exhibit weak metallicity dependence. So all of the stars here are from the theoretical one for BL Herculis only. Once again, they seem to show negligible metallicity dependence. There are a couple of observed empirical gamma terms here, but they have been estimated using only about 6 or 7 stars, which is quite a small sample. W Virginis and Arvitori, so Arvitori, especially if you look here, also seems to promise negligible gamma term. So it is extremely important to populate also the W Virginis and Arvitori from the observed spectroscopic perspective. For BL Her and W Virginis, we also have similar, this is from Marcella Di Crescenzo. So we also have negligible metallicity that is predicted. And lastly, for type 2 Cepheids, one of the most recent empirical observations from Chung Nigao seems to, for all type 2 Cepheid classes combined, they also seem to promise negligible metallicity effect on PL relations. So once again, this is the end of my slide, and I think WST will be extremely crucial because all of these theoretical estimates need to be compared with a homogeneous spectroscopic metallicity determination. That's it. Thank you.
Awesome, thank you. So it's very interesting, fascinating talk. I'm sure everyone else also in the audience liked the talk. So thank you, everyone. And now we're taking questions. If anyone has any questions or comments, or if you want to directly interact with Sushmita.
I have questions.
Yes.
Yep.
Thank you for your talk, Susmita. Can you go back? Can you please go back to your slide 6?
Yes. Yes.
Maybe you say this thing, but I missed. What are dashed black line and red solid line
Yes.
apart from the strip?
Yes. So because we have such a huge number of models to begin with,
Okay.
we did linear calculations first. So the red line and the blue line are the red edge and the blue edge. And the dashed ones are the
Something
linear
that
periods.
make me confused is your cut at 4 days. Now I understand the dashed lines. It is the cut at 4 days for BL Herculis, right?
Yes, so what we did actually
Okay.
was 0.8 to 4.2
Yeah.
days with the linear period, because we saw there might be some differences between linear and non-linear pulsation periods, which is why we allowed for 0.2.
No, because I usually put this cut around 10 days for BL Herculis.
Yes,
Said
so
in your
so what I did was I followed the convention that just a second. Yes, so I followed this convention that BL Her stars are 1 to 4 days and W Virginis are 4 to 20. So when you say a cut at 10 days, in principle, it would be BL Her plus the short period W Virginis combined together.
Okay, another question. I don't understand really how do you set the convection for your how is it treatment in your code for convection?
So this is like a whole topic, but
Yeah.
so what we did was in the MESA instrument paper, they started with 4 convection parameter sets. So because the whole idea, because say when we are dealing with modeling one particular star, we have to be super careful and calibrate the convection parameters well. So that has recently been done by Gabor Kovac, Robert Szabo's group. So that is also a super important aspect where you need to calibrate the convection parameter sets. But here, because we were doing general grids, is why we did the parameter sets that were already provided in the Paxson paper. For example, if you want to have a look, I can share what it looks like. So once again, even in the instrument paper, it mentions that we have to.
Okay.
Is it visible?
Oh, okay, right. Yes.
No, we can't see anything now.
Just a moment. It is
Or maybe it's loading, I don't know.
Yeah.
If you show me the here, okay, right, perfect.
Yes, so this is what is called. So we have all of these parameters here that are referred to as A, B, C, and D. So RSP alpha is the simple alpha that is the MLT, the alpha parameter that usually is changed from 1.5 to 1.8, right? In the other changes are all of these other parameters. So all of these are an interplay of different convection parameters, different alpha parameters. It could also be that they are not these particular sets of convection. It could be somewhere intermediate. So it's not fixed that one has to use these 4 convection parameters only. And as is shown, when we try to fit in one particular observed light curve, for example, we have to calibrate the convection parameters while simultaneously fitting light curve and radial velocity curves. I think even better is if one can simultaneously fit multi-band light curves, so ogle, Gaia, different passbands, right, as well as available radial velocity curve. So that is how one needs to calibrate. But when we are talking about grids, it made sense to use these convection sets. And so these convection sets, what I believe is, they can be a good estimate or a starting point before calibration begins. So we can have the nearest good estimate of the pulsation period and the light curve structure, and then try to start fine-tuning.
I need to read this paper to understand the difference between this code and Stellingwerth. Another question, do you have any plans for, as you know, Arvitauri represent a problem for modeling. Do you have any
Yes,
plans
yes.
for doing something in this direction? Because I think that maybe we can join forces to ask something like a grant, no? I think because
Yes, that
as you
is
know, we
actually a
do
wonderful
almost
idea.
the same
Yes.
research
Yes.
into different,
Yes.
we
Yes.
can think about this thing because
Yes. Yes. Exactly.
it's
Yes.
a complicated issue, Arvitauri, so
Yes.
maybe we can
Right.
join forces. Yeah.
Right. Yes.
Okay, thank you.
Okay, Robert,
Yes,
has a
Robert.
question. Please chime in.
Just a short question. Thank you. Very nice talk, Sushmita. Do I understand correctly that this is part of a new Indian LSST in-kind contribution? I heard something about this at last week at the LSST Europe conference. Or I misunderstood that.
No. So this is actually where we are already co-authors. So this is the summary of what was already published before.
Okay. Maybe
I think
I
maybe
missed
for
it.
that one we could be talking to Anupam. Is that like he's
Yeah.
engaged with
Maybe
that?
he's
Yeah,
the
no,
one.
right, true.
Yes.
Yeah, and there is a question on the Slack as well, on the chat box.
Chat. Okay, sorry.
Okay, Chang is saying, I'm wondering if you have any predictions or evidence about BL Herculis becoming a long-term binary member.
So W Virginis seem to be members of binary systems, but BL Her so far, I don't think we have had prediction or evidence.
Okay, thank you. And okay, any final comments, questions? Chang says thank you. Okay, so now I think we can wrap up this session here, and we're again thanking everyone for their participation, for your time, and yeah, like Sarah is also saying that thank you for your presentation. Interesting talk. Yes, we all enjoyed it so much. Okay, so see you around. Take care, and see you
Bye.
next time for the next talk.
Thank you so
Stay
much all
tuned.
for being here today.
Ciao.
Bye. Thank you.
Thank
Bye.
you.
Bye.
Bye.